Now here we will discuss on the slenderness reduction factor, that is alpha S. Now the slenderness reduction factor along with the moment modification factor, that is alpha M, both of them constitute combined factor to modify the value of MSX, that is the nominal section moment capacity, to determine the MBX, that is nominal member moment capacity. Now, this slenderness reduction factor, or the alpha S, represents how slender the segment or the subsegment is against the lateral torsional buckling. More the segment is slender, more the segment or subsegment is weak against the lateral torsional buckling. So by this factor, the nominal section moment capacity is reduced depending on how slender the segment or the subsegment is. Now let's look into the relationship on which this parameter depends on. Now here on the screen you can see I have taken this few important equations from the code AS4100 code. Now the first equation, that is for determining the alpha S, you can see in the relationship it depends on different variables, different other parameters, and one of them is M subscript OA, which is also known as MO, which is referred to as the reference buckling moment. Now, this MO, that is the reference buckling moment, again in turn depends on few other constants and few other variables. If you can see on the next equation, one of the important factor here is the LE that guides on um, that guides on determination of this reference buckling moment, which in turn affects the determination of the slenderness reduction factor alpha S. Now, so this LE is very important part here. Now this LE again depends on KT, KL, and KR. This LE is the effective length of a segment or a subsegment or a unbraced length, whatever you may call it. So you can see here that this LE is depends on three different factors like KT, which is known as the twisting restraint factor, KL load height factor, KR lateral rotation restraint factor, along with the actual length of the member, unbraced length of the member L. So let's see how we can instruct Staad.pro to determine this. Although Staad automatically determine these three factors internally, but one can also override the automated determination of this factor if he or she has any other reason depending on his or her engineering judgment. Now let's see how Staad or how one can define those factors here. Now here you can see on the left part this table which has been taken from the code, which represents determination or which guides the user to take the right values of the twisting restraint factor or the load height factor or the lateral rotation factor. Now if you just take a look into that, all of these factors depends on, very importantly, depends on restraint arrangement or the boundary condition of that segment, and along with few other parameters like the position of the load, then the geometrical attributes of the elements, etc. Now this restraint arrangement, as I have discussed before, can be defined or imposed easily in Staad.pro by the P-brace member if you have opted for the physical member design. Now we will understand more while we will with some working examples very shortly. Now these factors, as you can see, these factors, as I've mentioned, that these are determined automatically by Staad.pro, but an engineer can override the automated calculation if he has any other reason, or if he has done some hand calculation, or if he has any other engineering discretion. So all you need to do if you want to override those values, you need to use few parameters defined under this design parameter of AS4100 code implemented in Staad.pro. The first one is the SKL. That is, this corresponds to load height factor, that is KL. Next one is SKR, which corresponds to lateral rotation restraint factor, that is KR. And next one is the SKT, which correspond to twist restraint factor, that is KT. So one can one can select or one can define those parameters to replace or to disable the automated determination of this factor by Staad.pro. And in addition to this factor, this LHT parameter is very important here because if you look into the second table, you can see the load height factor, that is KL, has got to do with the position of the application of the load. By default, all the loads applied in Staad.pro is at the shear center, but in any case, if the load is being imposed any other place other than the shear center, for example, like top flange, then you need to change or update these LHT values. So if it is on the shear center, then you need to leave as it is because by default LHT parameter is taken as 0, that is at the shear center. But it is if it is applied at the top flange, then you need to take this LHT value as 1. And Staad is going to understand that okay, you have instructed Staad that the corresponding factors where this load height position has to be chosen from the top flange, then the Staad will automatically extract those values. So although you can define all those values from this design parameter dialog box, but one can also go to the input editor and define all those parameters by the command prompts in the input editor.